Chapter 13, Statistical Thermodynamics. In this chapter, we're going to focus on Boltzmann distribution. In previous chapters, we learned quantum mechanics, which deals with individual molecules. A macroscopic object contains enormous amount of molecules. Individual molecules of a macroscopic object will not have the same energy. Generally, there will be some distribution around an average. This energy distribution is important for us to understand the thermodynamic properties of a Borg sample. Thermodynamics of Borg samples deals with the average behavior of large numbers of molecules. And the statistical thermodynamics is the link between the microscopic properties of matter and its Borg properties. One of the key ideas in statistical thermodynamics is Boltzmann distribution, which is used to predict the populations of states in systems at thermal equilibrium. It is the impact of temperature on the state of system. Let's use a coin toss analogy to introduce important concepts, including configurations and permutations. A coin has two sides, head and a tail. When a coin is tossed, either head or tail shows up. When a coin is tossed 4 times, here are the possible outcomes. Maybe every time head shows up, that's called 4 head. Or every time tail shows up, so that's 0 head. Or head only shows once, that's called 1 head. So this can be first time head shows up, and then second, third, fourth time tail shows up. Or head shows the second time, or the third time, or the fourth time. So altogether we have 4 possible arrangements for 1 head. Now these are called configuration. So configuration can be 0 head, can be 1 head, 4 head, or 2 head. 2 head means head shows twice. It can be the first 2, or first third, first fourth, second third, second fourth, or the last 2. So altogether here we have 6 arrangements or permutations for 2 heads. For 3 heads, we have also 4 arrangements or permutations. Now for molecules, we'll talk about later, and these permutations or arrangement is also called a microstate. So here we have 16 altogether microstates. Now each of these permutations has equal possibility. So which one is the most likely outcome? Okay, because 2 heads has the largest number of permutation, and all these every arrangements or permutation has an equal possibility, and therefore 2 heads should be the most likely outcome configuration. In other words, if you toss coin 4 times, most likely you get 2 heads. We can calculate the probability of a configuration. This is calculated by the number of permutations associated with this configuration divided by total number of possible permutation. For example, the probability of 0 head, you should use the number of permutation of 0 head, which is 1, divided by total number of possible permutation. In this case is 16. So 1 divided by 16 for the 0 head. And for 2 heads, we use 6 divided by 16. So that's the largest probability for 2 heads. The most likely configuration outcome for a trial is the configuration with the greatest number of associated permutation. Let's now look at the chemical system. Quantum mechanics tells us that at the microscopic level, molecules or particles can only have certain allowed energies called quantized energies. Assuming epsilon 0 is the lowest energy, epsilon 1 is the second allowed energy, epsilon 2 is the third allowed energies, and assume the system contains n particles with total energy E. And this system may contain various possible configurations. A configuration tells us how many molecules occupy the lowest energy, how many occupy the second energy, and so on. For example, let's say we have total 10 particles. In reality, it should be much more than 10. So if we have 10, one possible configuration is we have 5 at the lowest energy level, and then we have 3 at the second energy, and 2 at the third energy. That adds up to 10 molecules. And we can write as 5 at the lowest, and then 3, and then 2, and the other energy levels are all 0, so 0, 0. So that's one possible configuration. Or we may have 4 at the lowest, 3 at the second, 2 at third, and 1 at fourth, and then 0, 0. So that's another possibility. So there are many possible configurations. The question is, which one is the most probable configuration at a certain temperature? Now, in the coin tossing analogy, we show that 2 heads, okay, is the most likely configuration because it has the largest number of permutation or arrangements. Similarly, here we want to find the most probable configuration that gives the largest number of microstate or permutations. Okay, so the configuration where we have certain number of molecules occupy the lowest energy level, certain number of molecules second energy level, and this configuration gives the largest number of microstates, and that's the most probable configuration. Before we find this most probable configuration, we need to remember that there are 2 constraints. One is the total number of molecules is fixed, n. N is the total number of molecules. So n0, n0, n1, n2 adds together should be n. Okay, so that's constraint 1. And constraint 2 is the total energy is fixed. So the lowest energy, let's say n0 times epsilon 0. So this is the lowest energy. This is the number of molecules occupy epsilon 0 plus n1 epsilon 1. That's the second energy, and this number of molecules has this energy. So this adds together, and so on. You add all energy levels, that give you the total energy E that is fixed. Okay, these are 2 constraints. Let's study a simple system containing 3 particles. And the total energy is 5 energy unit. So the constraints are total number of particles 3, total energy 5. And the allowed energy levels are 0, 1 energy unit, 2 energy unit, 3 energy unit. So these 4 energies are the only allowed energies for this system. And the question is, how do these 3 particles populate among these energy states? In other words, what are the possible configurations? Now, one possible configuration is that there are 0 occupy the lowest energy, and there are 2 here in the second energy level, 0, So 0 at the third energy level and 1 particle at the fourth energy level. Okay, in this way, the total particle is 3. So 1, 2. 1 plus 2 is 3. That's one constraint. And the total energy here, one particle has a 3 energy unit. 2 of them has 1 energy unit. So 3 plus 2 is 5. So that's a second constraint, 5 energy units. Okay, so that's one possible configuration. A second possible configuration is that 0 at the lowest energy, 1 at the second energy, and 2 at the third energy level, and 0 at the fourth energy level. In this way, total is 3. So 2 plus 1 is 3 particles, and the total energy, so because this one is 1 energy unit, and this is a 2 energy unit, this is also 2 energy units, 2 of them, so that's 4. 4 plus 1 is 5. So the total energy is a 5 energy unit. So that's the second possible configuration. And the third configuration is this. 1 particle at the lowest energy, 1 particle at the third energy level, and 1 particle at the fourth energy level. So 3 particles, total energy 0 plus 2 plus 3, that's also 5. So these are 3 possible configurations that meets the requirements that the total number particle is 3, total energy is 5, and the possible energy levels are these 4. And what we want to find is which of these 3 configurations is the most probable configuration. In order to find the most probable configuration, we must find out how many permutation or arrangements does each configuration have. So let's look at this configuration first. No particles at the lowest energy, 2 at the second energy level, 0 at the third energy level, and 1 at the fourth energy level. So we can write 0, 2, 0, 1. Now the number of ways arrangement is also called weight. If we label the 3 particles as A, B, C, then it is possible we have AB at the second energy level is still 0 at the lowest energy, but 2 AB at the second, and C at the fourth energy level. That's possible arrangement for this configuration. It is also possible AC at the second energy level, but B at the fourth energy level, or maybe BC at the second energy level and A at the fourth energy level. And these are 3 possible arrangements to achieve this configuration, where 2 particles at the second energy level and 1 at the fourth energy level. So the W is 3 possible arrangements. Now let's look at the second possible configuration, where no particles at the lowest energy, 1 at the second energy level, 2 particles at the third energy level, and 0 at the fourth energy level. Again, if we label A, B, C, then the possible arrangement is 3 also. You have AB at the third energy level, C at the second energy level, or it's the B at the second energy level, or it's the A at the second energy level, and BC at the third energy level. So W is also 3. There's a mathematical equation that allows us to calculate the weight of a configuration. Now for a general configuration, N0 occupying energy level epsilon 0, and 1 is the number of molecules occupying energy level epsilon 1, and 2 number of molecules occupying epsilon 2, and so on. For this configuration, the weight is calculated by this equation. The total number of molecules, factorial, divided by the product of the factorial of the number of molecules occupying each of the energy levels. So, and lowest energy level, and then first energy level, second energy level, and the third energy level, the number of molecules, factorial, and the product. Okay. Now, in the previous slides, we discussed a simple system where we have 3 particles, total energy is 5. We showed there are 3 configurations, and 2 configurations both has same weight, equals 3. And the third one here is when we have 1 molecule or particle occupying the lowest energy level, and 0 in the second energy level, and then 1 in the third energy level, 1 in the fourth energy level. So this is the third configuration. Let's use this equation to calculate the weight. So the so total number of molecules or particles is 3. So use 3 factorial divided by the number of molecules occupying each orbital, the factorial. So the first one is 1 molecule factorial, and then the second energy level is 0 factorial, and then here is 1 factorial, and the highest energy level is also 1 factorial. Now all these equals 1. 1 factorial or 0 factorial, they are equals 1. So this is 1. Now 3 factorial, this one means 3 times 2 times 1. That gives you 6. So the weight, according to this equation, is 6. So what are the 6 arrangements? Well, if we label these 3 particles as A, B, C, then these are the 6 possible arrangements or permutations. So this is A, B, C, means A occupy energy level, lowest energy level, B occupy third energy level, and C occupy fourth energy level. Or A still occupy lowest energy level, but B occupy the highest energy level, and the C occupy third energy level. So A, B, C. Or A is third energy level, and the B is the lowest energy level, and the C is the highest energy level. Or here A, B, C. Here A, B, C. A, B, C. So the last one, A occupy highest energy level, B occupy lowest energy level, and the C occupy third energy level. All right. So please confirm these are the 6 arrangements for the for this configuration. In summary, for the simple system where we have 3 particles, n equals 3, total energy 5 energy unit, and 4 energy levels, okay, 0, 1, 2, 3. There are 3 possible configurations. The first one is 0, 2, 0, 1. So 0 number of molecules in the lowest energy level, 2 number of molecules in the second energy level, 0 in the third energy level, 1 in the fourth energy level. Okay, 0, 2, 0, 1. Or 0, 1, 2, 0. So 0, 1, 2, 0. Or 1, 0, 1, 1. So 1, 0, 1, 1. So for these 3 possible configurations, the weight equals 3, 3, and 6. So because this configuration has the largest number of weight, and therefore this is the most probable configuration. So in other words, if you have 3 particles, total energy 5, and 4 energy levels, the most probable configuration is that one molecule has lowest energy, one molecule has energy 2 unit, energy unit, and one molecule has 3 energy unit. Let's use this column chart to show the importance of dominant configuration. For the simple system containing 3 particles, we showed that there are 3 possible configurations: 0, 2, 0, 1, which has a weight 3; 0, 1, 2, 0, which also has the same weight 3; 1, 0, 1, 1, which has a weight 6. So this is the dominant configuration because this configuration contains 6 arrangements. Now, if we increase the number of particles from 3 to 7 to 14, and you can see the number of arrangements for the dominant configuration becomes increasingly large compared to other configurations. Now, if we increase the number of particles even more, and you can see the number of arrangements of the dominant configuration is so large compared to other configurations that other configuration becomes insignificant, and this is as if the only configuration that you can observe. Now remember, a macroscopic sample of metal contains an enormous number of particles. For example, a cubic foot of air contains about 1 trillion particles. The weight of dominant configuration for this kind of sample overwhelms all the rest in importance, and the macroscopic properties will be characteristic of that particular dominating configuration. And this configuration, dominant configuration, is the Boltzmann configuration we are looking for. The dominant configuration is the configuration with the largest weight. So if we plot weight as a function of configurations, the dominant configuration should be at the maximum. And in calculus, at the maximum, the derivative should be 0. And in this case, the weight derivative over configuration should be 0. Now, configuration is the number of molecules occupy different orbitals, different energy levels. And therefore, we have many variables. The number of molecules at the lowest energy level is a variable. At the second energy level is a variable. All these are variables. And therefore, we should be able to write many partial derivatives. For example, if we have let's say two energy levels, then we can write W over N0 is 0, W over N1 is 0. So combine all these partial derivatives, we should be able to find N0 and N1. Now, if W is at the maximum, then natural log W should also be the maximum. So we can also, instead of find the maximum at W, we can also find the maximum at natural log W. It turns out that this is more convenient. So because W is this equation, the factorial of total number of molecules divided by this product of the factorials of the numbers of all different energy levels. So we add the natural log, and there's a Stirling approximation allow us to simplify this equation. So the natural log W equals n ln n, and this is the total number of molecules, and this is the number of molecules at a certain energy level I's energy level, and this is also the number of molecules at number I, so epsilon I. Okay, so remember the summation among all the energy levels, you add all of them. Okay, and so the derivative, okay, we show the derivative of this one over each of the number of molecules, number of molecules on the energy levels. All right, so for example, for I, then you derivative over I, Ni, and you should get negative natural log Ni over N. Before we go further, we need to introduce the constraints. Remember, the total number of molecules, it doesn't change, and total number and the total energy is also a constant. These are constraints. So assuming we have a function f with variables x1, x2, etc., and the variables has a constraint. So how do we maximize this function or minimize this function? In mathematics, it's called Lagrange multiplier problem. So instead of the partial derivative of a function over each of the variables to be 0, we need to add a multiplier times the constrained partial derivative over each of the variables. And these two added together is 0. So that's a Lagrange multiplier problem. And let's see an example. John happens to acquire 420 feet of fencing and decide to use it to start a canal by building 5 identical adjacent rectangle rounds. So 1, 2, 3, 4, 5. So you need to find the dimension of each round to maximize the area. So let's say the variables here is x and y, the width and the length x, y, and the area is xy. So we need to maximize this function xy. Okay, and the constraint is that the total length is 420. So total length y should be 1, 2, 3, 4, 5, 6. So 6y and 10x. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10x. These added together should be 420, or minus 420 equals 0. So that's a constraint. So you have a function, you want to maximize it, and there's a constraint. So according to this Lagrange multiplier problem, we need to partial derivative of this one over x and over y plus multiplier times this function over x and y. So here is the function. Partial derivative for x, partial derivative x. All right. Now partial derivative means you assume other variables are constant. So x, y, partial derivative over x means y is a constant. So this should be y. All right. So you get the first function is y, and this partial derivative of x. So y is constant, 420 is a constant. So you get 10. So 10 times lambda equals 0. Similarly, you do the partial derivative of y, so you get this function. And don't forget the constraint itself. So you have 3 equations and 3 variables. You can solve x, y, and the multiplier. In this case, x give 21, y is 35. All right. So with this dimension, you should get maximum area with the total number of length is 420 as a constraint. Let's come back to the chemical system where we want to find the dominant configuration. Because dominant configuration has the maximum number of weight, so the partial derivative of weight or natural log weight over configuration should be 0. And this is also subject to two constraints. One is total number of molecules is constant. The other is total energy is constant. So because we have two constraints, we have two multipliers. We use alpha and beta. So alpha and beta. So the partial derivative of ln W over Ni plus alpha of constraint 1 over Ni and constraint 2 over Ni equals 0. Okay, remember we have many of these equations over N0, N1, N2, etc. So the goal is to find this configuration to maximize the weight. Let's calculate this partial derivative. So the G is the sum of the number of molecules occupying all different energy levels. This will be N0 plus N1 plus arbitrary Ni, and then all the energy levels. And this add together minus N is 0. So the partial derivative of Ni means that this is a variable, everything else is considered constant. So the derivative of this function will only give you 1, others are 0. And so that's why this whole thing becomes alpha. Now let's calculate second constraint partial derivative of Ni. So this will be the number of molecules times the energy of a certain energy level. So this will be N0 times epsilon 0 plus N1 epsilon 1 plus a arbitrary energy level will be Ni epsilon I and so on, and then minus E. So the partial derivative of Ni, again, these are all constant, they are 0. All constant, they are 0. The only survive is this one, Ni epsilon I. This derivative over Ni should be epsilon I. Okay, and so that's why you have beta times epsilon I. So this equation now becomes partial derivative of ln W over Ni plus alpha minus beta epsilon I equals 0. According to Stirling's approximation we discussed before, the partial derivative of ln W over Ni should equal to negative n ln Ni over n. So this equation becomes negative natural log Ni over n plus alpha minus beta epsilon I equals 0. In this equation, Ni is the number of molecules occupying the energy level epsilon I. I is an arbitrary number, and n is the total number of molecules. And so this fraction actually is the percent of molecules occupying energy level epsilon I. And then this plus alpha, alpha is a multiplier that is to be determined. Same thing is beta times energy level epsilon I equals 0. Now we can rearrange this equation becomes ln Ni over n plus or equals alpha minus beta epsilon I, so that we can calculate this fraction Ni over n then equals E. So if you remove natural log, then this becomes exponential alpha minus beta epsilon I power. Okay, And so that's the new criterion so far in order to maximize W, or in other words, that's the dominant configuration. In this equation, there are two multipliers, alpha and beta, to be determined. And we realize that this is Ni, number of molecules for an arbitrary energy level I. So this applies to all the energy levels. When we can write N0 to N equals E alpha minus beta epsilon 0, and N1 E alpha minus beta epsilon 1, and so on for N2, N3, for all of them. Okay. Now, if we add all these equations, then the left side will become N is the same. The top is N0 plus N1 plus N2. You add all this together. So this is N1. And then you can write N2. So you add all together, and this N0, N1, N2 added together is N. So this becomes N over N is 1. So the left side is just 1. And the right side, they all have e to the alpha, e to the alpha. So if you add the right side, it should be e to the alpha and times e to the negative beta epsilon 0 plus e to the negative beta epsilon 1, and then add all energy levels. And therefore, we can write as 1 equals, okay, the left side is 1, the right side is e to the alpha summation e to the negative beta epsilon I. I is arbitrary, so you add all energy levels. That's this one. So by using this equation, we can calculate E alpha. So E alpha should be 1 divided by the summation of e to the negative beta epsilon I over all energy levels. And if we substitute into this equation, then we can remove alpha. And so we have Ni over total number of molecules equals e to the negative beta epsilon I divided by the summation of e to the negative beta epsilon I over all energy levels. Okay? And without the proof, here I show you beta, another multiplier, should equal to the 1 over 1 over kt. K is Boltzmann constant, is this one. All right. Now, if you are interested in how this is derived, please read a textbook or other resources. All right. So you can plug in this equation, and you get we call Boltzmann distribution, and that's the number of molecules occupy certain energy level can be calculated by the e to the negative ei, that's the energy occupying the energy level that you are interested, divided by kt over the summation of this equation over all energy levels. And this is called a partition function. We are going to talk more later. We just derived this equation to calculate the dominant configuration, where Ni is the number of molecules occupying epsilon I, all right, and equals e to the negative beta, which is 1 over kt, times ei, divided by the summation of e to the negative beta epsilon I over all energy levels. Now, this equation applies to the system where each energy level only have one state. Sometimes an energy level may have two states, and this is called a degenerate states. So for this kind of system, we need to include the degeneracy into the equation. So here, for this system, Ni divided by N should equal to the Gi is the degeneracy of energy state energy level I degeneracy times e to the negative 1 over kt times ei divided by the summation over all energy state, and the degeneracy is included for all energy state. Now this summation can be simplified using symbol q as called partition function. So this equation now we can write as Ni over N equals Gi. So I is arbitrary, so that's the energy level we are interested, and the number of molecules occupying this energy level equals the degeneracy of that energy level times e to the negative epsilon I, that's the energy of that energy level, over kt divided by partition function. We have derived the equation to calculate the dominant configuration called Boltzmann distribution. And we see that all microstates are equally probable. And there are many possible configurations. But this is a configuration that has so many microstates that it outweighs all other configurations. And that's called dominant configuration. And one has the greatest probability of observing a microstate associated with the dominant configuration. With overwhelming probability, one will observe a microscopic state of the system characterized by the dominant configuration. And this macroscopic state of the system is in equilibrium state. And Boltzmann distribution dictates the most probable configuration that will be observed. The law describes the energy distribution associated with chemical system at equilibrium. Boltzmann distribution allows us to calculate the probability of occupying a given energy level I, which equals the degeneracy of this energy level times e to the negative energy of this energy level divided by kt over a partition function, which is the summation of this equation over all energy levels. Now, if we calculate the ratio of number of molecules occupying I and K, two energy levels, and because they both have Q, they cancel each other. So we have Gi over Gk, and the E negative beta epsilon I divided by E to the negative beta epsilon K is equals to E to the negative beta, which is 1 over Kt, and then Ei minus Ek, so the power minus, which is delta E epsilon. Delta epsilon is the energy difference between K and I. This is delta epsilon. Okay. So this equation suggests that the ratio of I over K, number of molecules in I and in K, then this ratio is determined by this ratio is the energy difference between them over Kt. Now Kt is called thermal energy. In kinetic model, we showed that each molecule has a kinetic energy in average 3 over 2 Kt. So this Kt measures the thermal energy, the average kinetic energy. And so these equations suggest that the larger this number, the smaller this ratio, because you have a negative sign here. So the larger this ratio, the smaller the molecules occupy, the higher energy level. And this ratio is delta E over Kt. That's the comparison of this energy difference over thermal energy. So if this energy difference between these energy levels are much larger than the thermal energy, then the molecules does not have enough energy to populate the higher energy level. So you have a smaller number of molecules goes to the higher energy level. Okay, so the energy needed to populate a given energy level is compared with the thermal energy available to the system. The larger the energy needed, the less likely the level is populated. Boltzmann constant is the direct link between a temperature T and the corresponding kinetic energy, average kinetic energy of a microscopic particle. So this is the average kinetic energy of each particle, and this is temperature, and this is the Boltzmann constant. So Kt is a measure of this thermal energy. At room temperature, about 300 Kelvin, the value is 4.14 times 10 to the minus 21 joule. Boltzmann constant is also related to the ideal gas law constant R. So R equals K times Avogadro's number, which is 6.022 times 10 to the 23rd power. So K, you can calculate by gas constant divided by Na, the Avogadro's number. Let's apply Boltzmann distribution to a very simple system that has two energy levels. The lowest energy level is 0, and the second energy level is epsilon. What are the fractions of molecules occupying the first and the second energy level? Well, according to the Boltzmann distribution, the number of molecules occupying a certain energy level I should equal to the degeneracy of this energy level times e to the negative the energy of this energy level divided by Kt, and then divided by partition function, the summation over all energy levels. In this case, G is 1 because according to this diagram, the degeneracy is 1 state for both. So this is 1, okay, 1. And the first energy level is 0, and so we have e to the negative 0. That's the energy for the first energy level divided by Kt, plus the second energy level is negative epsilon. So that's this one. All right, divided by Kt. The summation over both energy level give you partition function. So this adds together is the partition function. The first term is 1 because e to the 0 power is 1. Now let's calculate the fraction of molecules on the first energy level, which should be this part divided by partition function. So this is just this energy level, and that's 1. So 1 divided by partition function. And then use this one divided by partition function, and that give you the second energy level. Now, if we look at the first one, this temperature at a very low temperature, so inverse a small number give you a large number, but then you have a negative sign, and that becomes very small. So at a very low temperature, this approach 0, and that means this approach 1. So that means at a very low temperature, almost 100% of molecules occupy the first energy level, which makes sense because if the temperature is very low, then molecules has very small thermal energy to populate to the higher energy level. Now, when you increase temperature, then these start to increase, so the fraction becomes smaller. That means the number of molecules occupy this decrease, and this decrease because some of molecules will excite to the higher energy level. So this will increase, this will decrease if temperature is increased. If we plot this fraction over temperature, Kt, then you can see at very low temperature, 100% at the low energy level, and 0 at high energy level. When temperature is increased, then the first energy level decrease, the higher energy level increase. Where at very high temperature, they approach 50-50%. So half of them remains at the low temperature, half of them is excited to the higher temperature. So the populations tend towards equality as temperature increases to infinity. At extremely high temperature, half of the particles are excited into the energy level 1, and the other half left at the ground state. Consider a system containing infinite number of equally spaced non-degenerate energy levels. For example, we learned vibration has energy levels equally spaced. And so the lowest one, energy 0, and then epsilon, 2 epsilon, 3 epsilon, and so on. So for this system, let's calculate the partition function. So partition function is the summation of Gj or I, the certain energy level of the degeneracy times e to the negative the energy of that energy level divided by kT, and the summation over all energy levels. So in this case, the first one is energy 0, and also the degeneracy is 1. So this is 1 for all energy levels. And the first one, energy 0, e to the 0th power is 1. So that's the first energy level. And the second energy level, energy is epsilon, and then 2 epsilon and 3 epsilon. So you add infinite numbers. And in mathematics, this summation gives you 1 over 1 minus e to the negative epsilon kT. Now, if we plot this partition function against temperature, so kT, temperature, and we get this kind of plot, suggests that the partition function increases when temperature increases. Initially, is 1, so partition function is 1 at temperature 0, and then it increases when temperature increases. With the partition function calculated, now we can calculate the fraction of molecules occupying a certain energy level using Boltzmann distribution. So here is the equation. So here is the Q we just calculated, plug in, and we have the fraction of molecules occupying certain energy level at a certain temperature. And we can plot it against temperature, so low temperature to high temperature. And at low temperature, for example, at a certain temperature Q, calculated to be 1.05. And the percent of molecules at the lowest energy level here shows about, let's say, 95%. So there's a very small amount at the second energy level, and there's almost no molecules occupy higher energy level. Now, when you increase temperature so that Q becomes 1.5A, then not only the first one, but the second energy level is significantly populated. Even third one has some percentage. Increase higher temperature to higher temperature, then Q becomes 1.99. So 1, 2, 3, even 4, fourth energy level is also significantly populated. Now at even higher temperature, Q increase, more energy levels are now accessible to the molecules. So at a very low temperature, only the lowest state is significantly populated. At higher temperature, upper states become progressively more highly populated. The molecular partition function here gives an indication of the average number of states that are thermally accessible to the molecule at the temperature of the system. Example, calculate the proportion of iodine molecules in their ground excited, first excited and second excited vibrational states. Now remember, vibration energy levels are equally spaced. So something like this one. So 0, epsilon, 2, epsilon, 3, epsilon, and so on. And this is also called a uniform ladder. And for the uniform ladder, we already calculated the partition function in the last slide. And the first one is called the ground state, and this is called the first excited state. This is called the second excited state. And Boltzmann distribution says the proportion of or fraction of molecules occupying energy level I should equal to E to the negative beta epsilon I. Beta is 1 over kT. Okay, so that's the beta. And divide by Q. Q is the partition function we just calculated in the last slide. So in order to calculate the fraction of molecules, we need to calculate the beta first, or 1 over kT. And so here is beta 1 over kT. So K Boltzmann constant, temperature 298 Kelvin, because the energy given is inverse centimeter. So that's the unit for the energy unit. In order to be consistent, we should convert joule to inverse centimeter, and that's the conversion factor. So beta becomes this number, 1 over 207.226 inverse centimeter. So plug in this equation, and for the first energy level, epsilon I is 0, so this is 0 and this is 0, and when you plug in these numbers, you get first fraction is 0.645. That's the first energy or ground state energy level, and the first excited energy level is epsilon. The energy is epsilon. So epsilon here given is 214.6. So plug in this equation, and also beta plug in. So you should get 0.229. And then the second excited energy level is 2 epsilon. So you should be this times 2, and plug in this equation. All right, so what you get is 0.081. So first one, the majority of the molecule is in the first the ground state, and then first excited is 22%, and then third energy level or the second excited state is 8%. So at room temperature, several vibrational energy levels are significantly populated. Now, if you compare the energy difference, so from ground state to first excited state, the energy difference is epsilon, which is 214.6. The thermal energy, if we convert to kT, convert to inverse centimeter, is 207. So these two numbers are comparable, means that molecules has thermal energy that's comparable to the energy difference, and therefore many molecules has enough energy to populate to the first energy level, and even some goes to the second excited state.